morning, everyone. No first days are typically going to be involving, the syllabus and getting us used to the stuff. I don't want to spend an awful lot of time in that. You can all read. You can go to this Canvas website and go through the syllabus. The thing's turning into a book. I mean, there are a number of things that are in there, but at least it's one location for everything. So I'm just going to give you the abridged version of the syllabus. We'll start off with contacting me. Will you please use, in your own email and my email when we communicate, use your Olympic College one. I know some of you have got your fredishere@gmail.com or whatever. Try not to use that one. I will be communicating once you're all finally in the Canvas shell. I'll be using the Canvas shell because I can do batch emails and send you things like, hey guys, the Zoom meeting's about to start, here's the link and things like that. So hopefully that'll go smoothly. You've done enough online probably by now that you're kind of used to the different ways of communicating. Email is obviously the only one that we really use. But I may choose to, depending on the problem that you've got, ask you to do a quick Zoom lesson. So it's a bit like dropping into my office. And it's so much easier if I just write things down and talk than trying to type something down in an email, because it's not really, they're not really math friendly. You know, it's quite hard to draw in an email some quite complicated math stuff. So we will do that. All the good stuff that you need to know, like joining WebAssign, is in Canvas. It's also in the syllabus. I did send out an email. I've sent out about 3 now, with the link. On the top of my head, what's the number? It's Olympic 1925 4658. So that's Olympic 1925 4658. And as I say, that's on an email that I sent out. It's also in Canvas and it's also in the syllabus. So if you go hunting for it, you'll get it. If you've used WebAssign before, then you know how it's going to work. Question?
Yes.
Yes. Where are you? Is it Lynn that just asked? Okay, go for it. What's your question? Nope, no question. None that I know of anyway. Where was I? God, I'm easily distracted right now. Yeah, so all your homework, all your tests, all that good stuff is going to be in WebAssign. Slightly different structure from Calc 3, if you had one for Calc 3. I'm breaking things into 2-week chunks. So the way it's going to work is when you go to WebAssign, everything you see there, you've got to until whatever it is, Sunday, October the 3rd, October the 4th. Sunday on the 4th, right? I'll just mute you all. That way we won't hear back conversations. So Sunday, 2 weeks work. If you see it in WebAssign, it's due, right? So the only things invisible on WebAssign are what's due in this 2-week period. After that 2-week period, Sunday midnight is due. That's it. You got to be proactive. You can't wait until Saturday and say, I'll do 2 weeks homework. It won't work. So you got to make sure you keep on top of it, because it will build up really, really quickly. Anyway, after the 2 weeks, we have a test. And that will be on Monday. And all Monday will be a test. And that will be on WebAssign in the usual way. And 2 more weeks test, 2 more weeks test, 2 more weeks test, and bum, 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 all the way through. I may choose to, I hope I don't need to, but I've got a schedule on Canvas that will tell you what's happening in each of the 2 weeks and the day of each test. So hopefully you'll be able to prepare for that and make sure that you're free. Final, of course, is, I couldn't tell you off the top of my head, but it's in the syllabus, so you can find out when that is. The final is cumulative, it's in everything. So that's how we're going to do things. So every lesson we'll try and cover some topic and things hopefully will work out smoothly. But if I have to, I will adjust stuff. So if I have to bring something in or move it to the next week, then we'll do that. It just depends on. It's hard to predict. I've been teaching long enough, and one of the things I know about teaching is that no two classes are ever the same. For some reason, we will go through line curves like it was baby stuff. And I'm thinking it's going to take us 2 days and it takes us 1. And then we'll hit triple integrals and it's just going to be pulling teeth. And I'll need to take 2 days when I thought I needed only to do it in 1, right? So I like the flexibility. So you just have to live with that. And I think that's just the best way to do things. So yeah, so you don't find out on Monday we'll do this and then Friday we'll do that. I think that's just too prescriptive. But there's 2 weeks we will cover this, basically. That's how it's going to work. If you're joining WebAssign, if you haven't got one, whatever, you need to join up really quickly. If you don't have your financial aid yet, you get 2 weeks free. So just join up anyway, use up the 2 week free, and then you still have to pay at the end of the 2 weeks, but at least that'll give you a chance for your money to go in. I think financial aid had a horrendous time on the summer where some people weren't even getting their money like 8 weeks into the thing. It was ridiculous. You got to sympathise with the poor people. That CDC link was just not their friend. I was at a meeting last week and they said it's better. Now, I don't know if better means you'll get it in 4 weeks or whether better means you'll get it when you should have got it normally. But hopefully 2 weeks will get you through it. That's my goal, my fingers crossed. If for some reason it's not working, I'll talk to WebAssign and see if we can get a little extension because of that. They're pretty good. So if I cry enough, they might do it for me. Okay, so that's that bit done. Canvas, great resource. Everything that we do is recorded, so every Zoom lesson will go there in case you miss one. The way I'm going to do attendance is going to be a little bit different. Sometime during today, I'm going to ask you to go to the little chat thing and just say hi or here or something. And I just need to look at the comments and I'll have a little time thing. And if you haven't said hi or yes when I asked you to, it means that you weren't really here. You just switched on the video and went and had your dinner. So you won't get credit for being here. Any questions before we get started? Are we good? We ready for fun? Okay, so let's start with the first one, a joke. We're going to start with the joke and hopefully finish the course with a joke and a few in the middle. I know Jodie loves my jokes, I can tell just looking. Okay, do you know I have cut 5,000 trees down in my career? I know that for sure because I kept a log.
Funny. Funny.
Let that one sink in. Or not, as the case may be. Okay. That was okay, Lee, wasn't it? It was that bad, it was good?
It was pretty punny.
It was pretty funny, I'll give you that. Okay, so it worked for my last class. No guarantee it's going to work. Yeah, it looks like it's working. You're looking at my white screen? Okay, so let's look at Calc 4. Let's do an intro to it. What is Calc 4 about? What do you do in Calc 4? Calc 3 was a kind of catch-all, wasn't it? Calc 3 was very bitty. It was a bit of this and a bit of that, and all sorts of pieces and leftovers and whatever. Important, but no real theme. Calc 4, on the other hand, is a very obvious theme. It deals with multivariate calculus. What do I mean by multivariate? I mean, in the usual Calc 1, Calc 2 world, there's a function. It's essentially a function in one variable, right? You plug in x and you get the other guy. It's sometimes written totally equivalent. It's sometimes written like that. Now, very, very crudely, wasn't Calc's one job how to differentiate this thing and what you could do with it? Right? How do you find derivatives and what kind of stuff can you do with derivatives? And wasn't Calc 2 how to integrate these things and what you can do with them? And Calc 3 was just bits and pieces, right? So what does Calc 4 do? Well, we are going to look at a function of more than one variable. There is an example of a multivariate function. There are two variables, x and y. Each one is independent of the other. In other words, x can be any number, y can be any different number, right? It looks like your cat's paying us a visit, right? So x and y, this is a multivariate function, sometimes written like that. And what are we going to do with multivariate functions? Well, we are going to do Calc 1 and Calc 2 things. We are going to find out how do you differentiate and how do you integrate multivariate functions, and what can you do with them, right? What are the uses of such things? So I kind of like the fact that it has a theme, right? It has a direction to go, right? How do you differentiate and how do you integrate multivariate functions? And we're going to start, the beginning of this course is going to deal with differentiation. And then we'll cover some stuff. That won't be half of it. That's like 20% of the stuff. And then the rest of it is going to be about integrating multivariate functions. Kind of cool? Now, how do you differentiate? Well, you've already seen it. Remember we did partial derivatives? Remember that? That's differentiation. When you differentiate a multivariate function, you don't call it a derivative of that function, you call it a partial derivative of that function. So we talk about partial derivatives. And we have some notation. So let's suppose the function is called x squared plus 2xy cubed. And if you want to do a derivative of this function, you have a choice. Do you differentiate it with respect to x, or do you differentiate it with respect to y, right? There's two variables. You could do one or the other. So we call them the partial derivatives. And the notation looks like this. Not a d in the usual way, but a kind of delta d, right? A little curved d. And that is the partial derivative of this function with respect to x. And to remind you how partial derivatives work, so this is kind of an overlap. You look at the function and you think of x as being the only variable in town, and any other letter of the alphabet you see, you treat that as if it was a number, a constant. So x squared is 2x. 2xy cubed, right? The 2 and the y cubed are like 25. So if you differentiate 2xy cubed, can you see that you get 2y cubed? Isn't it a bit like 2x gets you 2, 25x gets you 25, right? 2y cubed x gets you 2y cubed. That is the partial derivative with respect to x. It also has another notation that you'll see, which is f little subscript x. And it's the same thing, it's just another way of writing the partial derivative with respect to x. So that's what we're going to focus on for the next few days, how to find partial derivatives of multivariate functions. Of course, in this case, there are two, isn't there? Can I also get a partial derivative with respect to y? Now, if you take this function and you do a derivative, a partial derivative with respect to y, what will the derivative of x squared get you, if anything?
0.
0. And then if you differentiate this piece, don't you basically think of that as like 25y cubed, right? You just think of it as like numbers. So what you would do is multiply by the power, right? Reduce the power by 1. So you'd get 3 lots of this, y squared, and 3 lots of this gets you 6. Now, do you notice that in this partial derivative, there's still an x, right? The x's don't disappear, they just get considered as constant. So this guy here is like, I don't know, 5 squared. So its derivative is just nothing, right? So you don't write it. But in this case, you see how the x is kind of joined to the y cube, so it still lives. And of course, the notation for this guy is f of y, f subscript y. Is that ringing some bells? You remember going back and doing this partial derivative stuff, right? As long as you can have this mindset where you're able to pretend, if that's the right word to use, that one of the variables is really not a variable right now. It's just a constant that happens to be the letter y, or it's just a constant that happens to be the letter x cubed, right? Whatever it happens to be. If you can have that mindset, then these are not particularly painful. So let's just do some examples. I think you get the gist of it by practice, right? Which is what your homework is as well, right? Practice at doing stuff. So let's look at the partial derivatives. Of this guy. Okay, I've moved up the food chain quite quickly from a nice polynomial, which are pretty straightforward, to something with a little bit more meat to it. Let's do a partial derivative with respect to x. Okay, ignore that for a minute. X cubed sine y. It is not a product rule. Isn't it just a funny multiple of x cubed? Great? Just a funny multiple of x cubed. It's sine y, x cubed. So when I differentiate with respect to x, don't you just get 3x squared sine y? Okay, now let's look at this fella. You want to differentiate partial derivative e to the xy. Any suggestions? Differentiate e to the power of xy, partial derivative with respect to x.
Wouldn't it be like treating it as e to like the 2x or something? So you bring down the y, so it'd be y e to the xy?
Correct. You see how that's a good mind thought process? Just think of it as a 2 or something, right? Just say to yourself, if it was e to the power of 2x, wouldn't I get e to the 2x times 2, right? Well, it's not 2, but it's y, but it's just like a 2, right? It does the same job, do the same kind of things. What would that look like?
Y squared, e to the xy.
Agreed? Try getting into that mindset, right? If you have that mindset, it's not as hard as it might look. It might look, ugh, you know, but if you think about it, it's really just e to the 5x, isn't it?
Wouldn't that be e to the xy squared if it were y squared?
Oh, not that x, no. That x doesn't come out here, if that's what you're saying.
No, the y.
Oh, here?
If you changed it to y squared.
Yes. I just didn't write it. You nailed it, yes. Yeah, I should be careful when you change something to make sure you change the answer totally. Yeah, let's try a different fella. Let's do the Z, because they get written as Zs as well. And let's look at X sine XY, and this is really messy. And I'll tag on a Y cube just because I can. And I am going to do the partial derivative with respect to Y. The Y cubed is the easy one, right? I'm not even going to ask you for that one. This is X sine of XY. This is like 2 sine of 2y, right? Think of X as like a 2, whatever number you like. If you do a partial derivative with respect to Y here, won't the sine of XY get you a cosine of XY? What else will you get out of that? Won't you also get a times something?
Times X.
Times X. Isn't there already an X there? So when you put them together, can you see why that is an X squared? Does that make sense where that X squared is coming from? Now, what looks like almost the same question does actually involve a lot more work. Let's do the easy bit. Isn't the derivative of y squared with respect to x 0? Forget about it. On the other hand, isn't x sine of xy a product rule? Right? First product rule we've seen today, right? A product rule. So to do a product rule, I'm going to do the f dash g plus f g dash formula, right? I mean, that's the product rule. I just have to be a little bit more careful now because we're doing multivariate functions, right? That I'm really differentiating with respect to x here and not any other variable that might be happening. So this fellow would be the f, right? And this piece here would be the g. So differentiate with respect to x, x squared, and you get 2x. Leave the g alone, so you get that piece. So that's the first bit. Plus, leave the f alone, and now we're on the last piece of the puzzle. If you differentiate the cos, oh shit, and spice and
Yeah, we were doing it to the second one there.
I
right?
was doing it to not what I'm intended to do, but I guess I caught myself in time. So pretend that never happened, and we'll start again. This is the f, right? And this is the g. So differentiate this, you get 1. Leave this guy alone, you get the sine of xy. Plus, leave this guy alone, you get x. And now I'll differentiate the sine of xy, which definitely gets me the cosine of xy times something. If you differentiate, yeah, saw the mouth moving, right? Times a y. And you see where I stick the y. And really, you should never write 1. There is our answer. Now, when you compare the two different partial derivatives, the one with respect to x and the one with respect to y, there is quite a significant difference, isn't there, into the way they look? So partial derivatives of with respect to x, and then you do it with respect to y, there is no reason under the sun that they should look particularly similar, right? It's not that unlikely that they'll look quite different, maybe even a lot different, just because of what they are. So far, so good. How about our next fella then? How about I'll return to this fella. And So xy squared, the cosine of x squared y, I'll let you have a shot at it first. Find that guy's partial derivative. I'll give you, I don't know, give you 30 seconds. Okay, here goes. When I look at this function, the kind of questions I would ask myself is, what technique am I going to use to differentiate this? Is it just simply a power rule? Is it going to be a product rule, a quotient rule, a chain rule? You know, that's typically your choices. It's definitely, in my mind, it's made up of two pieces, isn't it? And this piece I'm going to call F, and this piece I'm going to call G. So I'm talking product rule. Now, within that product rule, technically, isn't there going to be some chain rule stuff? You know, when you differentiate something like cosine of x squared y, isn't that like a chain rule? You know, like the cosine of x squared would be a chain rule, right? That type of thing. So when I'm looking at this, I'll be thinking, okay, be careful, which is not one of my strong points. So if you differentiate with respect to x, this guy, don't you just get y squared? Like 5x gets you 5, right? Y squared x gets you y squared. So this piece here is y squared. You leave the second piece alone. So far, so good. Now, add. Leave the first piece alone. And the first piece is all of that, right? Now, differentiation of a cosine x squared y. Well, if you differentiate a cosine, you get a negative sign. So going to be a negative sign of x squared y. And this is where the chain rule goes in. Because don't you then have to differentiate x squared y? But x squared y with respect to the x guy. So x squared y's derivative gets you 2x y. And so I now have y squared, the cosine of x squared y, it's negative. There's 2xy merging with these, so that's going to get me 2x squared, a y cubed, and finally, the sine of x squared y. And I'm not doing it, but could you imagine you did the partial derivative with respect to y? As I say, we'll be doing this for a couple of days, so hopefully we'll get plenty of good practice at you know, working with it. Any questions so far? You feel there's a deja vu, you've seen it before, you're kind of familiar with it. Right, next thing's probably not going to work, but I'm going to try it anyway. Let's do the paper version first. In Calc 1 and Calc 2 and whatever, if you have a function written in that format and you wanted to sketch it, to graph it, you would use two-dimensional paper, right? And it would probably look something like that, right? And what does that say, right? Well, for any given value of x, there is a corresponding y value that you get by squaring the x and adding an x, right? So 1 squared plus 1. And essentially, if you took every possible value of x in the universe, wouldn't you end up with a continuous sequence of points that would generate that curve? So here's a bit that's not going to work. Maybe I'll get lucky. What does that multivariate function look like if you try to draw it or sketch it, right? Well, the first thing we have is that it's not a two-dimensional situation, it's actually a three-dimensional situation. And so what we do is, at least we attempt to do, on two-dimensional paper, the three-dimensional world. So can you imagine that is representing actually 3 dimensions? The x and y is like the flat bit and z is like vertical. I don't know if my pens will work, but I'll try. Can you imagine I'm trying to draw that situation? Now, a little bit weird, but we have to live with it. And it's mostly engineers' fault that there's a rule called the right-hand rule, which you do this funny thing with your fingers. And I don't know what it is because I'm not an engineer and I don't care. But evidently this finger is something else, and that's a torque. And you curve your finger, and if things go this way, torque goes that way. Or if you curve your fingers that way, it goes. It's called the right-hand rule, right? Because of you lot, the x and the y have to point outwards. What does that mean? It means that the x's go this way. They are coming out at you, which to me is kind of unnatural, because I kind of, if I was in charge and the right-hand rule didn't exist, I would probably have made the x-axis go this way. Doesn't it make more, it seems more natural. That would be x and this would be y, but it ain't, right? So we live with it. So there's the y values and there's your z values. Obviously, you go down this way, you go negative. You go this way, you go negative, you go that way, you go negative, right? And you go like that, right? Now, to show you the problem, there's many problems with this on 2D paper. If I wanted to plot a point, like, well, let's choose a point. Suppose I decided that x was 1 and that y was 1, right? Then wouldn't the z be 1 squared times 1 plus 1 cubed, which would be 2? Right, so you can imagine a random choice of x and y generates a z. And I can pick any x and y in the universe, right? So basically, you pick any point on the floor. And for any point in the floor, won't the z value be the height above the floor that that point would be? Now, if I did 1 along, 1 thing up, and 2 up, it would kind of sort of look like that dot. Can you imagine how hard it is to represent on two-dimensional paper positions of anything in 3D? But that's me done it on paper. So what does that guy look like if you did all of them? Can you imagine an English countryside with smooth hills and valleys? Like a cover that you've flipped and it's got a bump in it and it goes on, right? What you're looking at when you look at this, if you try to plot it, would be what we call a surface, right? A convoluted surface most of the time, right? And that's what it would look like. Now, nobody in their right mind could do that the way you could do this. I could do a fair sketch of this function myself without too much technology. I ain't going to be able to draw this picture, nor should you be expected to. But it would be nice if we could visualize it by letting software do it. So I'm going to leave this for a few seconds. I'm going to see, and this is where I keep saying I don't think it's going to work, but I'm going to try. And see if we can get this. Right. Are you looking at our Canvas site right now?
No,
Someone
just see you.
You just see me. Okay, so that's job number 1. is go in, go basic, and share Canvas site. Are you looking at Canvas site now?
Yes.
Yep.
Yep.
It ain't failed yet, because that was the easy bit. On my Canvas site, I have got a guy called GeoGebra online, right? I'm now going to click on that. It probably will disappear on you. Did it disappear on you?
Oh, still there.
You can see it. Oh. Are you looking at a three-dimensional version of the XYZ plane right now? So I'm going to go over here. I'm going to try and add Z equals X squared. Oh, let's just stop there for a minute. That's what Z equals X squared looks like. Now, what happened there is that the Y values had no effect on the Z value, right? If you look at that and I rotate it a little bit, can you see that in a lot of what, oh, stop moving. There, that's probably as good as it. Can you see that if you orientate it in one particular direction, doesn't it just look like Y equals X squared, but now it's Z equals X squared, right? Now, if I add to this, a Y, nothing much interesting happened. Then you go plus Y cubed. And then I click out. Whoa! Oh, it's not as interesting as I thought. But can you see what the surface has now got an orientation to it? It's kind of got a little hill thing going on. Depends on how you orientate it. There. Right, can you see it's kind of bulging out on one side? That's what that surface looks like. Now, I'm going to, this is pushing it. I'm going to try to do the sine of X plus the sine of Y. I hope it's in radians. If it's not, I may have to do some stuff. Oh, pretty cool. Can you see what we've got here is a lot of symmetry, but it makes sense, isn't it, going to repeat itself after 2 pi? Can you see that that would be a very, very, very simple modeling of some kind of sound wave? Or some kind of weird magnetic pulse? Can you see why three-dimensional or multi-dimensional variables are much better at modeling the real world? Because if you think about it, the real world is 3D, unless you're a weird physicsy guy, in which case it could be 4 or 11D, right? But string theory is 11D, right? Newtonian is 3D. Relativity, I think, is 4-dimensional, right? Because they have space-time. So, but can you imagine that would be a really good way to visualize things that are happening in the 3-dimensional world. So what we are doing when we do derivatives, partial derivatives, is we're taking the functions like this guy here, right? And if you do a partial derivative with respect to X, you're taking that shape and you're slicing it parallel to the X-axis at different Y values. And if you take your answer, you know, it's whatever it is, it's X cubed Y plus Y squared. If you plug a Y in there, aren't you just left with a function of X? So you're basically slicing it and seeing what the derivative would look like on that slice as you go through the shape. Now, how does partial derivatives help with finding things then? Well, take that hill there. See that one there that my mouse is pointing at? If you slice it parallel to the x-axis, don't you just get a normal big parabola? What's the derivative at the top of that hill?
0.
0. Now, if you slice it parallel to the y-axis, don't you get a very similar hill? What's the derivative when it's the top of the hill?
Still 0.
So if you have a surface, a multivariate function, and you're trying to find where's the top of its hill, right? then don't you find the first partial derivative with respect to x and with y? Don't you set them equal to 0, and then you have this horrible system of equations in two variables, x and y? And if you can solve when are they equal to 0 at the same time, haven't you found the location of your hill or your valley? Right? It could be a hole in the ground. So the analogy between one-dimensional calculus, derivative 0, and multivariate calculus, you know, two derivatives, in this case, x and y. Do you see that the transfer of how to find where hills and valleys are, right, are the same? So you can use it to find the maximum value of a three-dimensional function, right? For instance, do you know that one I just written, the sine of x plus the sine of y? Have you noticed that they all have the same height? And I'd like to know, how high up does that function go? Right, if that's a wave function, I guess, what's the loudest sound, right? The decibels. What's it, if that's what the Z was measuring, right? The decibels at that point, right? What would it be? Well, wouldn't I have to find when this guy's partial derivative was 0 and when the other guy's partial derivative is 0, and then solve, well, technically an infinite number of solutions, but couldn't I just solve for one of them, just find any one? I'd probably find that one there, right? It seems easiest to get. And then wouldn't I be able to plug in the value of x and y at that point, and that would be the z value at the highest point, or the lowest point, if I was interested. That is scary. That actually worked. I was 99% sure that it would either not work for us or whatever. This is part of Canvas. This is another reason I want you to go to Canvas, because if you're a visual learner and you do too much of the algebra, you start losing, what the heck am I doing this? Why am I doing this? What is this telling me? At least if you could go back in that picture and say, okay, I'm slicing it in the x-axis. This is what I'm finding, right? What the derivative would look like at various points on that slice. For every y, this is what the derivative function would look like. Okay, any questions about that? Pretty good. So I think it's time for us to return back and do some more examples. Oh, this is a good point for me to do it. Somewhere you have the chat box, you know, the little chat box thing? The time is 1:45, 10:44. So you have till 10:45 to go down there and say hi. And that's how I'll be able to tell that you were in class today. Or hello, or happy face, or whatever you feel like. We ready now? Okay, let me go back and share our screen. This guy here. I'll do a Z version again. I'm returning back to polynomials, which is that guy there. And I'm going to find the partial derivative with respect to x. And I'm also going to find the partial derivative with respect to y. That was easy. Now, you know that in Calc 1, couldn't you find second derivatives? Right. So it's not a surprise that you find second partial derivatives. So what does the notation look like? Well, that's using this notation, the subscript notation. Doesn't that just mean second derivative, right? With respect to x. So I will do the second derivative with respect to x, and this gets me 2y cubed, and I guess nothing, right? I guess I shouldn't have even written plus 0. Oh, don't write plus 0 when you do your homework either, right? I should have just written, That guy, agreed. Now, let's do the second partial derivative with respect to y. Well, if you differentiate this guy with respect to y, you get this, and you get nothing again, so I'll be consistent in my mistakes. You get 6x squared y. Yeah, no biggie. Couldn't you do third and fourth and 23rd derivative if you felt like it? But here's something that's not so obvious. You can also get that partial derivative. Right? Now, what does that mean? It means find the derivative of this fella, right, this one here, but with respect to y. So you use this fella here, and you do a partial derivative of this fella here with respect to y. And if you do this fella, you get 6xy squared, and you do this fella, you get 2. Now, what about that fella? Because isn't that also a second derivative, but isn't the order partial derivative with y first, then the partial derivative with x second? So first, second, right? So there's the first one, right, with respect to y. Now do this one with respect to x, and you get 6x y squared plus 2. Now, anytime you do a partial derivative with respect to x, and then you do a partial derivative with respect to y, we've seen that the two answers can be quite different looking, right? Which isn't surprising. What might be surprising is that these two are the same. Now, you could say, well, that was just luck, right? You just happened to pick an interesting function where that happened. But that's not luck. In fact, that's actually a property. And the property says this, essentially. If z equals whatever the function is, right? In this case, it was that one, but it could be anything. If this is continuous function, then these two fellas will always be equal. And that's called, I think it's called Clairaut's theorem. I can't spell good, and I'm 99% sure that's not how you spell Clairaut, but that's how you pronounce them. So it's Clairaut's theorem. And I'm sure if you go to the textbook or look it online, you'll get it. It's a very interesting and unpredicted property. I would not have predicted that was going to be true, right? In fact, it can be used as a very subtle way of, is my function continuous? Now, if you think, well, what does a 3D surface being continuous means? It means that it's like a nice flowing, you know, English countryside. What would be not continuous? Well, the kind of things in 2D world are not continuous. Can you imagine a surface that was two flat planes that went vertical on you? It wouldn't be continuous along that entire cut. Can you imagine little volcano ones where at one point the thing just grows up and it's got a singularity, right? It's like a volcano shaped thing. That would be a bad one. Yeah, can you imagine a piecewise function where you take a nice surface and somebody gave it a rip and a bend? Right, it doesn't need to be infinite. It just not. I think of it like driving along the surface. If I get killed, it's not continuous. Right. So if I drive along and there's a hole and I fall down, it's not continuous. Right. You can't have holes. Right. It's got to be from one place to the other. You've got to be able to travel along the surface without having anything blocking you or causing you injury. Right. So you can take a function that you do not want to even try and look at its surface, right? Just picture it. But shouldn't you be able to get its two partial derivatives? These two. The two second derivatives, right? And if you can get them and they end up being equal, then can't you use Clairaut's theorem the other way around? If the two partial derivatives are equal, the function must have been continuous. Right. If the function is continuous, the two partial derivatives will be equal. But if the two partial derivatives are equal, the function must be at least continuous at the point that you were evaluating it. Right. A lot of functions are continuous for most of their life. They just have a problem, along, the vertical asymptote line or that one little volcano place. So even in those cases, you should be able to find that the two partial derivatives are equal to each other. And you only have a problem at the vertical asymptote situation, right? Or at the dot where it looks like a volcano. Are we cool?